This is Faraday's law, putting into numbers everything we saw about electric generators last week. You can tell how old it is by the fact that they're talking about the back voltage from an electric generator with a curly E. Curly E stands for EMF. Well, we put this notation to shame on the very first day of the unit when we said that EMF stands for electromotive force, aka electromotive, not a force. It's voltage, people. It's not a force. But we've been writing it with curly E for more than 200 years. We're not going to stop now. If you know how much voltage your generator generates, you're going to want to know the magnetic flux. The voltage is the change over time. Calculus buddies, you can just see the first derivative coming right out of here. The change over time of the magnetic flux. Stands to reason that magnetic flux isn't going to be constant here, but that's what we said when we were running the generator. We said it was the change in the magnetic field over time. This is everything we saw in the app, in the sim, in the lab, in the generator of what changed the voltage coming out. First, there's this negative. Well, that has to do, as you can guess, with the sign of the current. It's going to turn out to be hugely important when we do Lenz's law and the reversed right-hand rule. But for the moment, just looking at the magnitude, we noticed the strength of the magnet, the number of turns in the coil, and the area of the coil. And all of those come together to make this otherwise useless critter called magnetic flux. Magnetic flux is Latin for flow, and we can give Michael Faraday a lot of credit, certainly a good deal more credit than the doofus who first called back voltage EMF. Faraday pictured the magnetic field the way you'd picture a flow of water. And Faraday said, what would we have to do in order to catch as much of that magnetic field as possible? And that was how he modeled the changing magnetic field. Here's the flux. Now you can see that if you've got a bigger bowl, you'll catch more of the flux. Bigger area, more bowls, more depth, you'll catch more. And your bowl very clearly has to be oriented at 90 degrees to the flow for maximum catching, because if it isn't, you're not going to keep most of what you catch. And if your bowl is parallel to the flow, you're not going to get anything at all. So here's the model of what we just demonstrated. Here's the magnetic field flowing in vectors like the stream of water. Here's A, the cross-sectional area of the coil, and N is the number of turns in the coil. You maximize the flow into the coil as you maximize B perpendicular to A. This is one of those cases I tell my pre-calcers about where it's incredibly useful to measure area as a vector. Yeah, pi r squared, the circle, we all know. The issue is how much of that circle is perpendicular to A. And I'm sorry to say, for those of you keeping score, that area is typically measured pi r squared, there's your scalar, with a normal vector. Why normal? Because we can see from a dozen miles off, both here and in the sail problem, torque, that all of the business is going to happen perpendicular to that plane, perpendicular to the coil, perpendicular to the bowl, perpendicular to the sail. I know it looks like a cross product, but the mathematicians don't even want to bother taking the cross product. They find the cross-sectional area, they put it perpendicular to the plane. So if you're looking to find B perpendicular to A, interestingly enough, that's going to turn out as B a cosine theta, where theta is the angle you can see here, factor how far away you are from a perfect 90. If you're 1 degree off from a perfect 90, you'll get a little bit less flow. You'll get a little bit less magnetic flux. If you're at a perfect 90, rock on. You are 0 degrees away from maximum flux, and you are good to go. So our full formula for magnetic flux starts turn by turn. You'll need a certain number of turns to take account of. There's our magnetic field. There is the vector cross product, checked that they are perpendicular. This is A rather than A to the normal, so we've got our NBA, formula for magnetic flux. That simplifies to what we were really after, that is the amount of voltage we would generate, N, number of turns. A, the area of a coil. Notice our lab results. Every time we increase the number of turns, every time we get a bigger coil. B, magnetic field. Check to make sure they are perpendicular. If they are, theta is 0 and life is good. If they're not, you got a problem with that. Now, see how all of this changes over time. In pre-calculus, we switch over to physics at this point and do this laboratory fashion. Things you can change include N, the number of coils. Specifically, the number of coils should clearly increase. Next thing you can change, A, the cross-sectional area of your coil, increase that as well. B, get a stronger magnet, increase the magnetic field, your generator will do business. Check, check, check. The only thing we have left is delta theta over delta t. And yeah, there's a cosine in there, but we're not quite sure what to do about that. We do, however, know that delta theta over delta t, change in angle over change in time, is what we once called omega, back when we were young and innocent and school was still in session. This is the rate at which things spin. You want to change your cosine theta over t. Well, I don't know how to do that without calculus, but I do know how to do it with a hand crank generator, and that just means spin it faster, which is exactly what we saw in the generator lab. Of a calculus turn of mind, and the first derivative holds no fear for you. Then keep track of that negative sign. You're going to need it. And take the first time derivative. Pull out that operator. It's not a fraction of, let's see, N. That's a constant. You don't need to do anything with it. A. That's a constant. You're not going to do anything with it unless you're rebuilding your coil in the middle of your lab. B. You're not running out to buy a new magnet in the middle of the lab. So the only thing left in business is cosine theta. Hey, what's the first derivative of cosine? Bless my soul, it's negative sine. Aren't you glad you kept schlepping that negative around here? So here is our set of constants and our lovely little negative sine theta. And as we said in the previous part of the lecture, we're assuming an angle theta controlled by how fast you're spinning and how long you've been spinning it. So if you want to close your loopholes and take the derivative of that, chain rule. Notice that if you're taking the coefficient with respect to time, not with respect to theta, you're going to have a nice chain rule there bringing out your omega, which means the voltage you generate is directly proportional to the number of turns in the coil. This is why the Motors and Generators Expo groups tend to have film festivals all weekend long. Wind 1,000 turns and then pass to your lab partner. Wind 1,000 turns and then pass to your lab partner all week long. The area of the coil, wind around a large nail rather than a small one. The strength of the magnetic field. The speed at which your coil turns. And there is our lovely AC operating sinusoidally with an angular frequency of omega. Faraday's law, ladies and gentlemen.